Hi, everyone. Some of you know me, some of you don't. My name is Thomas. I am an alumnus of Stellenbosch University. Right now, I'm based in Boston. And I was given the opportunity to talk a little bit about some of my work. Let's see. Go ahead and tell me, Ralph, can you see this first slide?
Yep, looks good.
Good. Okay. So I'm going to try and give a really high level, rough overview of some of the stuff that I think about and that I work on. And I'm going to try and cover both of these topics, but I'm going to mostly focus on coarse geometry, which is kind of the pure math that I do. So first things first, here's kind of where I'm coming from in terms of my background. So I have probably stolen the Stellenbosch logo, and I'll probably get sued for this. But I did my Bachelor of Engineering at Stellenbosch University in Electrical and Electronic. That's pretty standard. And during that time, I took one abstract math class with Zurab, who's on the call now. And one thing kind of led to another, and I ended up doing a master's in mathematics at Stellenbosch, mostly based in category theory. In fact, I was funded and based in the MIH Media Lab, which I'm told still exists, which is, you can take it from me, is a super fun place to work and live and get a lot of funding. It's not always the best place to do hard mathematical thinking. So as long as you've got yourself a nook somewhere in the department where you can really sit and think, yeah, it's a great resource to take advantage of if you can. And how did I do that? I basically sold them on the idea that category theory would help them organize their information systems. And by them, I mean the people who are funding me. But most of my thesis, at least, so that my thesis was 4 chapters, 3 of it was just solid category theory, and in the 4th one, I looked a little bit into possible applications. So that was cool. I then came to Tennessee, which is in the United States. It's in the south of the United States, and did a PhD in mathematics. And for those of you who are sort of just very new to like how the academic systems work in various countries, in South Africa and in Europe, typically what the structure goes that you do some kind of undergraduate degree, you then do, say, a short master's, say 2 years maybe, and then you do a PhD for 3 years, and you're engaged in research a lot of that time. And you're probably funded by some kind of bursary or scholarship. And there are huge exceptions, but that's the basic structure. In the United States, it works like this. You do an undergrad, and then you go into grad school, which is what they call a PhD, without a master's usually. And if you're in grad school, you are being paid because you are teaching. Not teaching sort of as a full lecturer, but you're kind of assisting a little bit. So I took about 4.5 years to do my PhD in Tennessee. And during that time, I was teaching a lot. I taught some linear algebra, and it was great. And during my PhD, I kind of switched focus a little bit from category theory to something called coarse geometry, which is going to be the main topic of what I'm talking about. So I won't go into like a lot of detail with that. And then after that, last year, I applied for a bunch of jobs, and I ended up at Tufts University doing a postdoc. And this postdoc's kind of interesting. I'm in a group called the Metric Geometry and Gerrymandering Group, which is what MGGG stood for in the first slide. And what we do in this group is we are interested in computational and mathematical approaches to problems involving redistricting, which I will try and explain at the end. This is a word that every American knows, but very few, I think South Africans might not know. Elections, basically, and civil rights. And so what I do here is kind of a mix. I do a little bit of pure mathematics, and I teach a little bit of pure mathematics. I taught topology the spring, and I'm going to teach again in the fall. So apologies for the seasons. Spring means March. But I also spend a lot of time working on a computer, coding, doing basic data science. So I'll try and touch on that a little bit. But the reason I wanted to sort of talk a little bit about it is to just say that, you know, being a double threat in your career, if you do want to be a mathematician, can sometimes help you end up in a place where you don't have to stop doing pure math, but you also have access to other things. And I've enjoyed this postdoc a lot, even more than I expected to. Anyway, so what are my research interests? Well, category theory, topology, coarse geometry, and geometric group theory. These are all my kind of pure math interests. Don't worry if you don't know what those words mean. A quick summary is like, it's the study of spaces, except category theory is kind of the study of the study of spaces. It's sort of a overarching structure. And but I'm also interested in redistricting, elections, and data science. So I'm pretty proud of the left-hand picture, because the left-hand picture involves all 4 of those topics: category theory, topology, coarse geometry, and geometric group theory all at once, which is nice. I won't explain why though. And on the right-hand side, I have a picture of a US state, which is Pennsylvania, and it's colored red and blue for Democrats and Republicans. So those are the kind of pictures that I study. Okay, so I hope that everyone has discovered the hand raise feature, or that you will just unmute yourself and ask questions halfway through, because I want this to be kind of informal. All right, so I'm going to start with this one. What is this space? Well, it's a cup, right? It's a coffee cup. But there's this old joke that you might have heard, which is that a topologist can't tell the difference between a coffee cup and a donut. And we can try and understand what that means. What that means is that if the donut was made out of clay, you could mold a coffee cup out of that donut without tearing it apart. And you can kind of think how you do that, right? You got this round donut, and the donut is the hole in the donut is going to be the hole in the handle. So that's one half of it. And then you take the other half and you squish it into the cup. But you don't have to tear, you don't have to make any new holes. There's only one hole in the donut, there's one hole in the coffee cup. So you're pretty good. All right. But what this drives home, this old sort of really slapstick joke, is that what matters in the study of spaces is the question of when are 2 spaces the same, right? And that is kind of the key way to understand topology and coarse geometry from a high level. So here's a question which I was really hoping I'd be able to get some answers on. So let's try it, and if it doesn't work, it's fine. But I've got 3 spaces here, and I'm going to introduce them to you and tell you what they are, and then I want you to tell me which of them is the odd one out. So the first space is the one that's labeled 0, 1 at the top here. And that guy is all the real numbers between 0 and 1, but not including 0 and 1, right? So 0.5 is in there, like 1 over square root 2 is in there, like, but no negative numbers and nothing bigger than 1. In the second space, labeled R, this is all the real numbers. And you can think of this as like a one-dimensional infinite line going in both directions. So that's why there's little arrows on the edge, it's going in both directions. And then I have the so-called integers. The integers are all the whole numbers, negative and positive. So 0, 1, 2, 3, 4, all the way up. And -1, -2, -3, -4. And so if we draw them on a number line, they're like dots, which are a certain distance apart. They're going off in another direction. So does anyone want to unmute themselves and tell me which one they think is the odd one out?
Well, I guess integers is the odd one out here.
Why?
Well, you can make a direct mapping between the real numbers and the interval of 0 and 1 because it's a dense set, while the integers is just countably infinite. So you can't really make a direct mapping from integers to reals.
Very good answer. Okay, so the person who answered that, and I can't always tell who's talking, but whoever it was knows enough mathematics to know that there are a lot more numbers in the first 2 than there are in the last one. But that's kind of complicated because they're both infinite. But yes, that's a very good answer. Does anyone have a competing answer? No? Okay. Feel free to jump in if you like, but
Thomas, may I use this this question as part of assessing my honors students in taking topology class who are attending the talk?
Sure, happy to help. Honest students.
But I think you have to go on now.
I have to go on.
I think I'm making progress, yeah.
Okay, sorry, I thought that you were going to use it right now as an evaluation.
Yes, but it didn't work.
Didn't work, okay. So now that all the honest students have failed, we are going to talk about the next thing. No, but seriously, that's a very good answer. So that answer is what topology says. Topology says that the real line and 0, 1 are similar. Yeah?
Yeah, I'm trying to refresh so I can see it. I'm saying nothing.
Is someone asking a question, or they just unmuted themselves?
Do you see it? I don't see it.
Okay, I'm just going to carry on, but if someone has a question, let me know. So topology says that 0, 1 and the real numbers are the same. And we're going to see in just a sec exactly in what sense that's true. Well, I'm not just going to leave it there. But topologists will say things like, look, real line and the 0, 1, they are both connected. Connected means roughly that you can walk from one point to another without having to hop. Okay? For those who have actually taken topology are now complaining at me because it's not exactly that, but that's fine. For now, it means you can walk from one place to another. So if I give you any number between 0 and 1, you can walk to the other one along the line. Same here. If you were a little person trying to walk along the integers, you'd have to make some pretty big jumps. You'd have to jump one every time. And so they say, of course, you know, look at it, it's obvious. Coarse geometry's answer is completely different. Coarse geometry says, you know what? 0 and 1 is a bounded space. Two people living in 0, 1 are never more than 1 unit apart. On the other hand, in the reals and the integers, you can be infinitely far apart. So how can you possibly think that 0, 1 is the same thing as the real line? Okay, so that's a different perspective. And I'm going to explain exactly in what sense that's true as well. Okay, so let's look at topology. And I'm going to try and explain to you why the real line is the same as 0, 1 for topologists. So we need the definition of a continuous map. Now, I've debated whether to use actual epsilons and deltas here. And just given that not everyone might be a math major in the audience, I decided not to. But if you know what continuity is, put your definition here. A map between spaces, so taking the points in one space and matching them in the other space, is continuous if it can be done without making tears. But you are allowed to stretch and squish, okay? A sort of intermediate way of explaining this is that points which are very close have to go to points which are very close, okay? So let's look at an example of a continuous map. So I want to explain what's going on in this picture. On the top, I have 0, 1, and the bottom, I have the real line. And what I'm doing is I'm kind of taking this line, this little line at the top, and I'm stretching it until it hits the bottom. And I'm stretching it infinitely big, right? Like I'm taking every point there and I'm stretching them further and further apart until eventually they cover the entire real line. And that might seem crazy if you've never seen this, that you can do that. But in fact, you already know of a function that goes from a bounded set to an unbounded set, and that's called the tangent function, tan of x. So if you take tan of x and you do something like this, you get where you need to go. And you can see that I'm stretching infinitely. I'm really stretching out this little line, but I'm never tearing it apart. I don't have to take this piece and put it there and this piece and put it there. Okay. Here's another example. I could do the opposite of that. I could squish that real line in, right? And again, it seems kind of weird. Like, how can I fit this whole real line in there? But it's fine. I just squish it more and more and more towards the ends. And I never reach the end of the real line. So I just keep squishing more and more and I put it all back. And this is kind of based on the inverse of what I just said. So if you don't believe me that these can be done, I can draw you graphs of these functions. But you can sort of imagine that at the very least, the most you're going to be doing is squishing things. And in fact, these two maps, when you write them down properly, are inverses of each other. Doing the one, then the other, gets you back to where you started. So if I'm a point like in the middle, I go down and I go up again. If I'm a point so near the end, I go there, but then I come back again. So I've got a stretching one way and a stretching another way, and they make the identity, is what we say. They get you back to where you started when you're done. And the term for this is called homeomorphic. If you can do this with two spaces, have a continuous map in one direction and the other, so that they're inverses, they're called homeomorphic. In other words, they're the same space. That's what topologists would say. All right. And so now I've explained to you precisely why the topologist says that the real line is the same as the 0, 1. Great. Okay. So we've kind of explained the old joke. If you take this idea of morphing without tearing and you apply it to this situation of a donut, solid donut, and a coffee cup, you can do the same trick. You can find a map and back. And it might be quite hard to describe, but it exists. Okay. Now so that was kind of like the early 20th century point of view, that the real line is the same as the 0, 1 line. Let's look at a different point of view, which, to be clear, I'm making sort of I'm pretending that they're contradictory, but of course they're not. They're just different perspectives, which are useful in different ways. We're going to talk about coarse geometry and why is the real line like the integers. And for that, we're going to throw away continuous as an idea, and we're going to bring in something called bornologous, which I know the name sucks. We're kind of stuck with it. Someone invented it in like the early 2000s and we're stuck with it. A map between spaces is bornologous if the following thing happens. For every number r that you pick, there's a hard limit on how far apart points which are r apart can be stretched. Right? So you should think of this like distortion. There's distances in your one space which are going to be mapped to your other space. And you want to know that those distances don't get distorted too badly. So here's an example which is not bornologous. This map right here, the stretchy map. Right? Because if I take points which are 0.01 apart, in the middle, they're being sort of almost perfectly preserved, but then towards the end, they have to be stretched further and further apart. I'm stretching it out infinitely. There's no bound on how much I'm stretching points apart. So this is not an example of a bornologous map. So already we can see the difference. So what is an example of a bornologous map? Here's an interesting example. The rounding off function is bornologous. So everyone knows how to round numbers. I think this kind of comes up pretty early. If you've got 4.2553, you can round that off to the nearest integer 4, or 5.688882, or whatever I wrote there, that rounds off to 6. And this rounding off gives you a map from real numbers to integers. And I've kind of tried to depict it here, right? Like the blue little squares are all the maps, all the numbers that get mapped to that particular integer. And this is horrifically discontinuous. It's not continuous at all because we're tearing apart people, right? We're tearing apart 4.4999, not recurring, but 999, and 4.5. We're taking them to completely different numbers. And you can see that these little blocks, which don't overlap, even though they kind of look like they do, are being torn apart and put to these little integers over there. However, you can convince yourself that you're never changing distances between points by more than 1 when you do this map. Like if your two numbers were about 1 apart, they're never going to be more than 2 apart when you map them. Let's think about it for a minute. Like what's the worst that can happen? You can take 4.49 and 4.51. Those numbers are really close, but they're going far apart, but never more than 1 apart, right? The one's going to 4 and the one's going to 5. So this is kind of a good one to like take home with a pencil and just check that you believe that points are never being stretched further apart than they were +1. Another good example is, this is very basic, and this is continuous as well, is just to take your integers and map them right back to the real numbers, right? 1 is a real number, 2 is a real number, so map them back. And in fact, these two are not inverses of each other, right? If I start with 4.2, I don't get back to 4.2, I get back to 4, if you follow the little track. But they're almost inverses of each other. Doing one, doing the other gets you close to where you started. In fact, it gets you within 1 unit of where you started. And this is the condition that we require to say that these two spaces are coarsely equivalent. The top space and the bottom space are coarsely equivalent. In other words, they are the same space, according to a coarse geometer, for example, me. All right? And so now we sort of understand why that these two different perspectives is because each of them has a different idea about what a map is between spaces. One of them says continuous, you can stretch as much as you like, but don't break. The other one says you can break it a little bit, just don't stretch it too much. And you get different notions out of this. The sort of intuitive idea here is that if you look at these integers here, these little dots, and you walk backwards, and you keep walking backwards, eventually you won't be able to tell the dots apart and it'll look like a line. In fact, those of you who are in computer science know that this line is not actually continuous, it's a bunch of dots as well. So that's the idea, is that you're stepping back and you're looking at the integers from far away. And that's what gives you the right idea. Okay, so who cares? That's a good question to ask in mathematics. Why do we care to think about coarse equivalence? I mean, topology and the idea of a continuous map goes back to the early 20th century, and it's one of the biggest fields of mathematics. It's brought us a huge amount of advancement over the last 100 years. And it's been going on before then, but I'm talking sort of post-Lebesgue. But where do these ideas get applied from coarse geometry? Well, they're kind of more recent. Like, you're really only going back to about 1998 for the really good stuff that came out of this. And one of the sort of sets of good stuff that came out of this was studying manifolds. So manifolds are especially nice spaces. In fact, if you think of a space in your head, like a space, which is not outer space, but it's like just an object, you're probably thinking of a manifold. What I've got on the screen here is one. It's a space that looks, when you're standing right on the space, it looks like you're just in a flat plane, or you may be in three-dimensional space, or higher dimensional space. And it turns out that what a really cool thing to do is to take a manifold and do calculus on it. And things you think are true don't hold anymore, right? There are lots of fun things that can be true that you wouldn't think. For example, you might think that the only function with a constant derivative has to be sort of a straight line, but that might not necessarily hold depending on where you are. And so but this is what we refer to as differential geometry, for those of you who know what this is. Now, one of the big things that happens with differential geometry is we want to study how many holes there are in a space by only doing calculus. So the way to imagine this is, suppose instead of actually being able to look at the space, like look at this guy right here and count, oh, there's a hole there. Imagine if all you knew was wherever you're standing, and in fact, you have to know it everywhere. So if all you knew is at every point in the space, what is the curvature? Where's the curve? How does the space look locally? Does it look like I'm sitting on a hill? Does it look like I'm sitting in a valley? Does it look like I'm sitting on a saddle point? And it turns out that you can get from that information to how many holes are in your space. And this is something called the Gauss-Bonnet theorem. And there are lots. Yeah.
So do you only need the curvature at each point, or do you need the metric for the manifold?
The curvature kind of relies on the metric. So
Yeah,
when I say,
Is only the curvature needed, or do you need more than that? Do you need the entire metric at each point?
To get the Euler characteristic, which is what I'm talking about, number of holes, basically, you only need the curvature in a certain, for manifolds without boundary. You need the so-called Gaussian curvature. So it's like it's one invariant of the metric.
Okay.
Yeah, so that was a lot of gobbledygook to a lot of you, but it's a good question. Basically, the point is, how much do you have to know about this manifold in order to do what I'm telling you? And the answer is, you have to know a lot, but not everything. And that's kind of the space we like to live in differential geometry. So by all means, go look up the Gauss-Bonnet theorem. The reason I'm talking about the Gauss-Bonnet theorem is that the Gauss-Bonnet theorem is like this little prototype for something enormous called the Atiyah-Singer index theorem, which is this gorgeous sort of important, famous contribution of 20th century mathematics, which tells you something way more general than that. It takes calculus and tells you topology in sort of some big sense. And I'm not going to get into why, because it's just not that easy to motivate. But the main point that I want to drive home is that this gorgeous, amazing theory works for small manifolds, for bounded manifolds. Okay, so it works for spaces that are finite in some sense. The word is actually compact. It means that you can look at them and they're sort of one thing. They don't go off into infinity and forever. And so if you want to pass beyond the small guy to the big guy, it's not super surprising that what you need to do is talk about big spaces. You talk about the large scale structure of spaces, and that's exactly what coarse geometry does. So, okay, that was a lot of hand waving, but I was trying to explain one direction that this can go in. And I'm happy to talk more about that later. Okay, here's another place which I really like, and I think is super accessible and fun, is group theory. So those of you who have taken a first course in algebra might have seen groups. Groups are little algebraic objects that encode the symmetries of spaces. That's sort of a good way to explain it. And they're often introduced as just algebraic things. They are sets with rules where you add and you subtract things, and there are some axioms that hold. Kind of like if you've seen what a vector space is, if you've done engineering mathematics, a vector space is a group. You can add things and subtract things, but it has a bit more going on for it. And just as you don't think of the two-dimensional vector space R squared as just a bunch of random numbers that you can add and subtract, you think of it as the plane. It actually turns out that there was a big revolution happening in group theory when people started to think of groups as spaces in their own right. Okay. In other words, we're not just doing algebra anymore, we're doing geometry. It's not quite the same thing as algebraic geometry, don't worry. And there are many ways to do this. And for those of you who kind of want to get a flavor of this, this picture in front of you is the free group on two generators viewed as a space. And so if you know what that is, you know what you're looking at. How exactly this is the free group on two generators is a super fun topic, and I'm happy to talk about it more. But the point is that these spaces are just about as big as the groups that they represent. And the groups are usually infinite. We think we understand finite groups because 10,000 pages worth of papers have convinced us that we understand finite groups. That's debatable. But what we're interested now is understanding infinite groups. And if you want to understand infinite groups, you need to understand how they look from looking at them from a distance. And so it's really powerful to be able to use things like coarse geometry to apply to studying groups from a geometric point of view. Okay, so how do you do coarse geometry? Well, this is actually cool because this is kind of how you do math as well, in some sense. And this is only one way of doing it. There are a million ways to attack this, but this is kind of the way that I'm doing, and I think I can explain it. Topology has existed for 100 years, and people have been working tirelessly to develop a whole bunch of theory and machinery in it. Coarse geometry has existed for like 20 years max. So a really good idea would be take topology, take some inspiration from something going on in topology, and try and write it down as a coarse geometry concept. And we've already seen that, actually, right? We already saw that continuous map became bonologous map. So this is kind of a process which works, and this is the kind of things you get. Covering dimension, that's something from topology from like the 19-somethings, becomes asymptotic dimension, which is super important. Asymptotic dimension ties into like big C conjectures, like the Novikov conjecture and the Gromov-Lawson conjecture and good stuff like that. Homology or cohomology, you don't need to know what that is, but what you need to know is it's a topology thing that counts holes. Becomes coarse homology and cohomology. And homotopy becomes, guess what? Coarse homotopy, right? So the idea is take something from topology that's super old, turn it into something from coarse geometry that's super new. So for example, here's an example from my work, which is sort of one of my papers, which I think is kind of easy to explain. There's this idea of connected spaces in topology. And here I've got a little, I stole this from Wikipedia. There's a space called A, which is green, that's connected. And remember, I think I already said this, but connected means you can walk without jumping from any point to any point. The space B, the blue space, is not connected because you can't walk from any point to any other point. All right. So what I wanted to do is I wanted to take this idea from topology, connectedness, and I wanted to turn it into a coarse geometry idea. And I needed an intervening language to make sense, right? I mean, you can define anything you like, but you want to define it sensibly. And so the intervening language I used was category theory. So in category theory, we know what connectedness means. You can talk to any bunch of people. In fact, connectedness is this whole thing that waving my hands at it. If you take connectedness seriously enough, you invent Galois theory and category theory. It's sort of a very natural thing to talk about in categories. And so the reason I wanted to use categories is that there are two categories. There's a category of topological spaces and a category of coarse of spaces, metric spaces, that we call the coarse category. So if you don't know what category theory is, that's okay. All you need to know is it's like an intervening abstract framework, right? It's like when if you're an engineer, if you're doing control theory and you're doing systems and signals, they share this common language of differential equations. Well, topology and coarse geometry, we can bridge them by using this common language of categories. And so I ended up inventing this idea of coarse geometric connectedness, which I don't have a good name for because someone already stole the name coarsely connected. And it turns out that to be coarsely connected has nothing to do with whether you can walk from one point to another. It has to do with in how many directions are you going off to infinity. So this space above the line is supposed to be like a parabola that kind of goes off to infinity, or filled in, that only has one way to go to infinity, and that is connected in the coarse sense, the coarse geometric sense. And this guy below here has two ways to go to infinity. For those of you who happen to know what ends are, it's pretty much that, except you have to be a little bit careful with weird spaces. But for most nice spaces, you're counting the so-called ends of the space. How many ways are there to go off and never come back? Okay, so that's an example of the kind of thing you can do. Here's another example from some of my work. A big question in topology is, when can you take a map, usually a continuous map, from a subset of a space? So this little triangle is like living inside the space, and I've figured out a way to map it, to map it onto this little comma-shaped space. How can I ever extend that map? In other words, can I decide where all the rest of the space goes in such a way that I still preserve where this one goes, right? So can I make this jump? Right, so I start with just that. Can I do that? I don't know, it's not super obvious whether you can do this in topology. But the answer is that you can in a lot of cases, and the shining example of a theorem of this kind is the Titze extension theorem, which was proved by various people, but in this current form, I think it's Urison who proved it in about 1925. So if you have a normal topological space, if you want to throw away the words normal and topological and just replace them with nice enough, you have my permission. If you have a nice enough space and a nice enough subset of it, then any function can be extended as long as that function goes to 0, 1. Okay? So you don't have to understand all the words in this theorem, but I want you to make the comparison with this theorem, which I wrote with my advisor, which is, let X be a large-scale normal space. So this is going to be another kind of special that I'm not going to introduce, but it's modeled on the normality in topology. And then for any subset, in fact, and any slowly oscillating function, and these are not Bornologous functions, they're kind of like cousins of Bornologous functions, it extends over the whole space. And the reason I kind of wanted to mention this is, again, we used a unifying framework. We didn't just prove the second one by itself. We actually unified the proof of these two theorems and a third one from Katetov from back in the 50s, using a single language called a neighborhood operator. And neighborhood operators have already been the subject of research at Stellenbosch University. For example, David Holgate and his students have been looking at that for a while from the categorical point of view. So this was definitely something that I was mostly aware of just because I'd been at Stellenbosch. And it turns out that using this framework allows you to unify a lot of stuff. And why do we want to unify? Well, mostly it's because we want to get clarity. We want to understand the proofs, but also because, you know, if we've got a nice proof, maybe it applies to other situations. All right. When I talk about neighborhood operators, I should especially mention Ando Razofindra-Koto, who was a PhD student at Stellenbosch, I believe. And last I heard of him, he was at UWC, though I don't know where he is now. I'm sure Zurab.
Still there. He's
Okay.
still there.
He wrote a very nice paper on categorical neighborhood operators, which definitely inspired sort of this approach. Okay, so what are some of the stuff I'm interested in? Yeah? Some of the stuff I'm interested in right now is warped cones. So these are super cool. These are awesome spaces. So this is an incredibly low-res image that I stole from Wikipedia, I think. Apologies. But I made up for it by putting a complicated, completely unexplainable formula below it. So how do you make a warped cone? I'm going to give you a recipe. You start with a space of your favorite kind, and it mustn't be too big, sort of a small space. So maybe like a donut, which is called a torus in mathematics, or you can take a sphere, maybe some kind of some complex, a bunch of polygons together. And then you want to blow it up. So what you do is you stick it in some high-dimensional space, maybe a 3-dimensional space, and you take all the lines through it. So you can see what's happened here, that the green triangle is going to be blown up into this triangular cone, and that's what we call a metric cone. That's your first step, okay? So you've already taken your tiny space and you've blown it up, which is great, because what we're interested in, remember, is spaces in the large, like we're interested in that large scale behavior. But then you do something extra. You have a group acting on your space. A group just means you have a bunch of symmetries of the space that you've chosen, that you've decided are your special symmetries. And what you do is you build shortcuts into your space corresponding to those symmetries. So if any of you have ever heard of taking the quotient by a group action of a space, so this is kind of a high level concept in topology, but if you've heard of this, then that's not what's going on here quite. You're not quite identifying points. Instead, you're just making them pretty close. And that's about as much as I can say without using the words finitely generated. But basically, you're taking the space, which looks pretty okay. Like it's pretty normal. I think we understand it. And then you're building in shortcuts into the space. So it's like, it's kind of like tunneling from some kind of sci-fi fiction thing, right? I can get from here to Cape Town, maybe by finding a wormhole to Joburg and then driving down. So it's that kind of shortcuts that you're building in. You're jumping huge spaces with short distance. Well, it turns out that these things were introduced in 2003, and the reason that they're cool is that you can get counterexamples to things you think are true in coarse geometry. For example, there's this big conjecture called the Coarse-Baum-Kohn conjecture, which shouldn't really be called a conjecture anymore because we know it's false. And one of the counterexamples comes from a not too ridiculous version of this construction. You just need to know what a Lie group is, I think, and then you go Lie algebra, then you get there. And so I'm super interested in these spaces, and I've written one paper on it where I study sort of the functional analysis of these spaces. That is a super broad way to describe what that formula at the bottom is. But there's a C star in there, and that C star stands for C star algebra. So C star algebras are super cool algebraic things, and I won't talk about them at all because they're kind of technical. But anyway, I'm having a lot of fun playing with these warp spaces, and so is everyone else, so that's cool. Okay. I'm going to try and pull a little a bait and switch here, a little switcheroo, and talk about a different aspect of my research, which is not really related to pure coarse geometry. But I'm going to kind of relate them in philosophy. And the reason I want to talk about this is I just want to give a full picture of sort of the kind of different things I think about. So that it's not just pure coarse geometry and topology, but I also think a little bit about data. So let me try and motivate it this way. What is this thing in front of us? Do you remember the first slide I had was, what is this? And it was a coffee cup. This is another one. What is this? So let's look at some answers. A topologist says it's a bunch of points. Okay, like
It's the coffee.
Yes, it's what the coffee's left behind. It's just a bunch of points living in space. Like if you know about topology, and I'm sorry that the points are overlapping, but that's the computer. These points don't overlap. They're just points. You know that this is just a discrete space and nothing special about it. In fact, if I took all these points and I completely rearranged them, they would be the same space to topologists. Okay, but coarse geometry doesn't do any better here. He says, look, it's bounded. There's finite distances between every 2 points. I should say there's a finite bound. There's a finite diameter on the space. So it's nothing. I don't care. If I walk away far enough, it looks like a point. I don't care about this. And a computer says, well, it's a bunch of data, but it's not correlated. It's not on a straight line. So I don't like it either. So what is the solution? The solution is to look at the medium scale. In other words, not to look so closely that they look like points, not to look so far away that it looks like 1 point, but to look somewhere in between. And this is kind of the basic idea behind something called topological data analysis. And topological data analysis is about applying old topological ideas from like the early 20th century to uncover the shape of data, right? So if you're doing some machine learning, you know, this is the kind of thing that you might incorporate. But it's really new and doesn't have a ton of applications that we really care about yet. It's got some, I mean, people have been trying it out in cancer research with some success, things like cognitive neuroscience, things like speech recognition, those kind of things. But it's still kind of waiting for someone to do something with it. I don't know if, none of you are old enough to remember probably when neural networks, okay, none of the students are old enough to remember when neural networks were nothing and were just an idea that some PhD student had. But now they run Google. So TDA is in that first phase. It's not running Google yet. What do I do with it? Well, one of the things I do with it is I study something called redistricting. And just a brief explainer on that. In South Africa, when you go to the polls and you vote for your party, you vote for the party, and then the party gets so many votes and they get so many seats in parliament and they get to choose who goes there. This is sort of proportional representation based on a partyless system. America does not do things like that at all. In America, what happens is that you in your state, and state is kind of like, Americans like to pretend they're a country of countries. So state is like a small piece of the United States. They divide it up, like you've seen here, into these different colored regions. And then every one of those colored regions, you only get to vote for one guy. But you know who you're voting for. And when you voted for that guy, you send him to in this case, the House of Representatives, and he goes and votes on bills for you. And sure, like most of the time, whether you vote for someone is going to depend on whether they are Republican Party or Democratic Party. But in theory, you're voting for one person. Okay, now the upside of this is, I guess, that you probably are voting for someone whose door you could in theory go and knock on, you know, so that's nice. The downside is that how you draw these lines can actually completely change how Parliament looks. It's as if you can take this map, redraw the lines, and completely change how many people from each party end up in Congress. And this, changing the lines to make sure that you get as many people as possible elected, is called gerrymandering. And it's a huge problem and a big controversy, and honestly, a super interesting field of research. Because all the things you think are simple are not. And I'm not going to really explain what I use TDA for, but I'm going to throw up a fancy looking plot and gesture at it and say that basically I use TDA to study where the votes concentrate when you do redistricting. In other words, which districts are being won by who and how do they compare to their neighbors? And you get cool plots like this, which I can't really go into, but I'm happy to talk about anytime. And I think that's my last slide. So thank you very much for the opportunity to talk a little bit about the stuff I do.
Cool. Thank you so much. So we can open the floor up for questions, if anyone has any.
Sorry, can I ask again about the connection between coarse geometry and differential geometry outside of just the bounded manifolds?
Sure. So basically, so let me try and explain. So, okay, by the way, who's talking right now?
I'm Jean.
Oh, hi. Nice to meet you. So do you know, so I feel like you know a little bit about differential geometry.
Yeah, I studied some physics using it, so through that, I know a bit about it.
Okay, so the best way I can explain it to you is that, do you know what it's hard. Do you know what a differential operator is on a manifold?
I have a rough idea, but not like a concrete one.
Okay, so basically differential operators are like, if you've done calculus, right? If you're sitting in like first year engineering math, I hope you've seen DDX, and you know what DDX is. But DDX is a very simple version of what you can do on a manifold. On a manifold, you can do a lot of DDXs. You can do them in all kinds of different directions, right? Like you have partial derivatives in R2, you have all kinds of different stuff. So a differential operator is like a super generalized version of that. It's like an operator which satisfies certain axioms that you want from differential calculus. And what you're interested in is studying the topology of the manifold using these differential operators. And basically that's what the RAM cohomology, if you know what that is, that boils down to, basically. So it's finding holes in manifolds using calculus. And the souped up version of that is the Atiyah-Singer index theorem, which tells you how to relate the topology of a manifold with something called the index of a differential operator. And that works for compact manifolds. And if you want to generalize it, then things get complicated, because it used to be the case that the index of your differential operator was a number. It was like 2 or 3 or 4. And that told you basically something about like the topology. And you just cannot do that anymore in non-compact cases. There's no well-defined way to do that. In the Atiyah-Singer index theorem, you can't prove it. It doesn't work because you need things to converge in the right way, and they just don't. And so what you're left with, the best option you have is replacing that number with something much more complicated. And it has to do with something called K-theory, which is this super hot field of topology / functional analysis. And it turns out that what you stick in the K-theory, doing my best, what you stick in the K-theory has to do with the large-scale geometry of your manifold. In particular, it doesn't care about small holes. It only cares about big ones. And so in other words, you want to graduate your understanding of differential operators from compact case to non-compact case. And the only way to do that is to understand coarse geometry.
Okay.
That's the best I can do right now. I mean, I can try and send you a monograph on it, which is sort of high level, but it depends on what you've seen.
Yeah, I've only done differential geometry on pseudo-Riemannian manifolds because that's what's used in physics. So my knowledge of anything further is a bit limited.
Yeah, so I'm talking about Riemannian manifolds. I'm not even doing pseudo, but I'm talking about complete Riemannian manifolds here.
Yeah, pseudo-Riemannian manifolds is just one of the signs in the metric is flipped, since you want the concept of time. Yeah.
So,
Thomas, may I ask a question?
Sure.
So the way you motivated the idea of coarse space, I couldn't pick up much difference between how one might have motivated concept of a metric space or a uniform space. Could you please explain the difference between these things?
Yeah. So you're saying you mean what's the difference between doing coarse geometry and doing uniform space things?
So what are the structures that coarse geometry studies? What are they? Are they some kind of generalizations of uniform spaces, or?
They're kind of dual to uniform spaces. So all the applications are for metric spaces. And so just like you're basically caring about metric spaces, but certain kinds of maps. But if you want to graduate beyond that to the abstract framework, it's if you know either definition of a uniform space, what you need to do is you need to replace. So let me quickly try and sketch this a little bit. Uniform spaces are spaces where
I think we can forget about uniform spaces. So, but you're saying that coarse geometry studies metric spaces. Then is that what you're saying?
Most of the applications are in metric spaces, but the abstract framework is based very strongly on uniform spaces. What you do is you just reverse a couple of the axioms. So if uniform spaces are supposed to generalize things which are refined by epsilon balls, if that makes sense, then coarse spaces are supposed to generalize covers which are refinements of R balls. So you don't want positive Lebesgue number, you want bounded diameter.
Okay.
Does that
so what's the difference between R ball and epsilon ball?
Well, so the epsilon ball you think of as living inside your cover, so positive Lebesgue number, but the R balls you think of as being greater.
Oh, okay.
Coarser.
Got it. Yeah.
So that's kind of there's a duality between these two things, basically.
And the term bornological that you mentioned, I think I've even forgotten, but this term is certainly old term, but is it in a new sense that it has been defined in the beginning of 2000, or?
Yeah, there's a confusing fact that a bornology is a different thing. So bornology is supposed to be an axiomatization of bounded sets, and again, for reasons which they shouldn't have done, they called these maps bornologous. And so bornologous and bornological are actually different things.
Okay.
Unfortunately.
Thanks. Yeah.
There are better words for this. I think large scale continuous is one of the better ones, but this is what we're stuck with.
Mm-hmm.
I have a question. Can you hear me, Thomas?
Sure, I can hear you.
Hi. So thank you very much for your talk. I just wanted to ask you a question about your notion of connectedness, and maybe if you could just elaborate a bit more on how you adapted this topological connectedness to this connectedness of your notion of connectedness. Are you unraveling this categorical connectedness in a certain category, or what's happening there?
Yeah. So the idea is there is a notion out there of connected object in a category. Yes. And it makes sense in a huge number of categories. You only need some very basic structure and you can write it down. And then your question becomes, okay, I can take a category and I can take my connectedness idea and I can apply it and see what stuff is connected according to this category. And in topology, it turns out to be exactly what you want in the category of topological spaces. But then there's this other category called the coarse category. And this category has some interesting stuff. So what the precise definition of it is that you have your objects are metric spaces and your maps are bonologous maps with an extra condition that if bonologous maps are close, if their values differ by a bounded amount, then you identify them. And if you do that, and if you take that category, you check that it's a category, but it is, and you take your notion of categorical connected object and you look inside the coarse category, you can actually write down very specifically what things are connected. And that's how I came up with the definition.
I see, okay. And just to follow up, is this category that you discussed now, is it an extensive category, do you know?
An extensive category. Zilup's going to kill me, but I'm going to ask you what that is.
It's if you coproducts are disjoint and universal. So if you have a coproduct diagram, as in this central diagram here, if you pull back each of the coproduct inclusions along F, then the resulting diagram at the top row would be a coproduct.
Interesting.
So in this sense, this categorical connectedness, I don't know which connectedness you're talking about. Is it where homming out preserves coproducts?
Yes, that's pretty much that.
Yeah. So in this extensive context, it's where that notion of connectedness coincides with the kind of normal one where the connected object will be where every coproduct diagram, one of the coproduct inclusions is just trivial in the sense that one of the components is initial. So
okay, yeah, we're on the same page. Fantastic. Yes, I did used to know what that is, I promise. So the answer is yes, but you don't have pullbacks in this category, so you can't write it down the way with the pullbacks. But it is true that the sort of maps factor definition is the same as whenever it's isomorphic to a coproduct, then one of them is trivial, basically.
Okay.
Good question, though.
Thank you.
Can I ask another question?
Sure.
It's a bit advanced question, so I apologize to the audience. As you know, there is this Lovier's work where metric spaces are seen as categories, as enriched categories, where home set is a number. Do you think that one could generalize coarse geometry in this way, from moving away from metric spaces and going to enriched categories? How much of the real number structure do you need?
Yeah, so the answer to that is yes. And it was done. I don't know if it ended up being published by a colleague of mine at grad school. Basically, the right context is a enriched category, which is enriched over, I'm trying to figure out whether I want to say quantiles. So it's right. These are like ordered sets.
Typical framework, yeah.
Yeah. So I think that the answer is that they might even be the same thing. I can't remember exactly, but that's kind of, it's definitely possible to view coarse spaces as enriched categories. Yeah, and I've seen it done. I don't know if he published that eventually or not.
Thank you.
So right at the end there, where you're talking about the gerrymandering, what type of questions do you get to answer with TDA that you wouldn't be able to do before?
Yeah, good question. So some of the questions, one of my sort of favorite questions that I like to answer is, here's the general question that you want to answer, and then I can give you kind of a specific example. So the motivation comes like this. You've drawn these districts and they have certain outcomes every election. And what you want to know is, like, did you draw these districts weird, or did you behave yourself? Did you draw them sort of like any normal person would, or did you carefully draw the lines to favor your party or your race even? And the answer is that that's super hard to check, because the way to check it is to compare the map against every other map you could ever have drawn and see where it lies. Like, that's like really one of the few sensible ways of doing things. And the set of all maps on a state like this is intractably vast. Like, if you had to enumerate it, it would be the heat death of the universe. It's NP everything. And so you kind of have to explore it with very clever sampling techniques. But even once you've explored it with sampling techniques, you've got a huge number of maps and you don't know how to summarize them. Like, if I gave you 100,000 different maps of North Carolina, how would you know, like, what do they have in common and what do they differ by? And what the TDA tool allows you to do is extract some common features. That's kind of what I'm showing here, right? Like, I can tell you very basically what's being shown on the left-hand side is, on the left-hand side, I'm showing where is the district that gets the most Democratic votes out of 1,000 different plans. And it's sort of like, oh, it's always here, not too far from where I'm moving in January, over here in a place called Durham, North Carolina. So the question you can answer is basically, firstly, what are the basic expected normal features of a plan drawn by someone who's trying to be neutral? And secondly, you can answer the question, okay, and how does the plan that maybe someone is taking to court, how does that differ, right? Like, what I've shown here is actually the third plan that North Carolina has had in the decade. And to be clear, they should only have one a decade if they're doing it right, because the other two got thrown out of court. And if I had to show you the other ones, you would be amazed at how ridiculous the shapes get. And like, this line does weird things. And what TDA is able to do is to really nail down, like, where exactly is weird stuff happening in these maps. And that's sort of one of the things that comes out of it.
Thank you. Okay. If there are no other questions, then I guess just thank you, Thomas, for taking time out of your day to talk to us. It was a really interesting talk, very different from what we've had the past few weeks.
Sure, I appreciate it. It was great fun.
Thank you very much indeed. May I ask?
Cool. Well, thanks everyone. You have a good day further.
Take care, everyone.